Hello and welcome. Did you know I have been working on a game? In fact, I have a whole series about me working on the game. And over this time, I've come across many ways to make my code faster. And many of these have really surprised me. Thanks to folks like Glenn Hewlett, Curtis Boyle, Simon Jonason, William Astle, Steve Bamford, and Darren Atkinson's amazing 6809 programming guide, I have learned all sorts of ways that your 6809 can be improved. I've collected what I consider to be the top 3 rather unsurprising optimizations you can do in your 6809 code, along with 8 rather surprising ones that threw me for a loop when I first discovered them. And number 8 in particular was quite a doozy. Now wait, don't skip ahead. I know you want to, and I know this video is rather long, but you gotta watch it in order. That said, you don't have to watch it all at once. You can watch just one optimization a night, and in that way, you can spread your Coco Town joy through the week and beyond. Okay, let's get started with the top 3 rather unsurprising ways to speed up your 6809 code. The direct page register lets you use direct mode addressing as opposed to extended mode addressing. Let's say I have a variable defined here, and it's sitting at 3FOF. How expensive is it to load, store, or increment at that address? 5, 5, 7 cycles respectively. And if you look at the code generated, you'll see the entire address 3FOF is included in the instruction stream. But if we use direct mode addressing, that high byte can be skipped. The most explicit way to ensure you get direct mode addressing is by telling the assembler you definitely want to use direct mode addressing. This less than sign will do that. So how expensive is this load, store, and inc? 446. So they're each 1 cycle shorter. And again, if we look at the instruction stream, no 3F anymore because it knows the 3F comes from the DP register. It will use the DP register as the high byte and then use what's in the instruction stream as the low byte, and then it forms the address. So it forces the code to be smaller and the cycles to be shorter. But there is a price to pay for this. You actually have to initialize the DP register to be that high byte. Otherwise, you're making promises that you're not keeping. And there's no load instruction to load the DP, so you have to do it in a roundabout way. You could do it using the stack, or in this case, I'm using the transfer instruction. And this is not cheap. 2 cycles to load A and another 6 cycles to transfer it into the DP register. This means that the number of memory accesses that you're converting from extended mode to direct has to be so many that they dwarf the number of times you need to change the value in the DP register. At a minimum, you want to be doing 8 memory addresses that you upgrade to direct mode for each time that you have to run this sequence of instructions. For example, in the assembly language sound series, the final code made extensive use of the DP register. Every hsync interrupt, it was worth it to spend those 8 cycles to set up the DP, because if you check out all these highlighted less than signs, you can see how many loads and stores and decks and everything that made use of direct mode addressing. When every cycle counts, you want to use it. This is the one piece of advice I am not yet following for my game, because I don't yet know how I want to take advantage of DP. Will I want to use it exclusively for sounds? Will I want to just move all of my variables to be on a single page and then keep DP pointing to that page? Maybe I want to do it both ways. I'm going to wait until I have more of the basics done, and then I can do some comparisons and figure out how best to take advantage of it. I made a couple changes related to this. First, I had a counter that would count up to 3 so that I would move the background, like the mountains or the buildings, only once every 3 frames. So I would start the counter at 0 and then increment it, and then when it got to 3, I would clear it again. Every time you find yourself changing something and then doing a compare, you could ask, maybe I could do this differently. Maybe instead of counting up, I could count down. Instead, I could start at a 3, that's what I store, and then I decrement it. Now I don't need a compare to ask if what I ended up with is negative, or positive, or 0. Similarly, if you have a variable that's tri-state or dual state, make use of negative, positive, and 0 values. For example, the get joystick routine for joy Rx, it only cares if the joystick is left, right, or middle, so by using differently signed values for each choice, I can avoid a comp. When checking whether the car should slide, I can simply do a load, and then immediately ask if what I loaded is negative or positive. No comp necessary. The reason all of this works is because many instructions will set the condition code bits for you without the need to do a separate comp. Structure your values appropriately and you can avoid the extra comp cycles. There were a couple places in my code where I would use an absolute 16-bit value as a counter. One of them is the progress through a level. I would count the number of frames and then decide at a certain number what to do at that point. Add a rock, add a hole. And so I would associate with each action that counter number, and it would just keep going up and up and up. I had to make it 2 bytes, otherwise I would run out of frames very quickly. And I did something similar when it came to the bullets that are shot by the car. I didn't want bullets to be shot too quickly, so I would have an absolute 2-byte counter that told me how many times this has been called, and I would do a bit of math to see if enough of those counter ticks had transpired since the last time a bullet was shot. Both of these uses of 16-bit absolute counters could be turned into 8-bit relative countdowns. For example, in the progress through a level, instead of having an absolute frame number, I could just give a relative number of frames to count down. So this is now saying, after 10 frames, do the rock. After 10 more frames, do a hole. After 10 more frames, do another rock. Now I only need a single byte here. And similarly, I now have a car bullet countdown that only needs 1 byte. Here it gets reset to 10 after new bullets are shot. Here I check to see whether the countdown has gone down to 0, in which case it's all right to check the button for new bullets. And here I decrement it. This is a highly simplified comparison, one where I'm using a 2-byte counter and one where I'm using a 1-byte countdown. Code might do something like this. It might load D with the value of the counter, compare it with some 16-bit threshold, and if it has met the threshold, we'll go do something. Otherwise, we add 1 and store it back. In the 1-byte world, I might load a register with the 1-byte countdown, decrement it, then I can immediately ask if it's 0, and if so, do something. Otherwise, I store the new value into the countdown. The total difference is substantial, 27 versus 15. Every load and store, we're saving 1 cycle. A 2-byte compare is fairly expensive when we're going into extended mode addressing. And even the register math to add 1 versus subtract 1 is a difference in 2 cycles. Okay, now that we're warmed up, let's get into those 8 surprising ways to speed up your 6809 code. This first surprising optimization I'm going to talk about turns out to be the first surprising optimization I had ever heard about. As I was getting used to the 6809, I kind of categorized the registers as having primary purposes. A and B are for math, adding, subtracting, shifting. X and Y are for indexing. S is your stack. And U is another stack. So if you want to do another stack, you got another stack pointer for yourself. So in particular, if I needed a pointer into memory and I might be offsetting off of that pointer, I would use the index registers, X and Y. But not all index registers are built equally. How many cycles does it take to load into X or Y? If you're doing immediate mode addressing, y takes 1 cycle longer than x. Direct mode, y is 1 cycle longer. Indexed, 1 cycle longer. Extended, 1 cycle longer. Weirdly enough, U, which I thought was mainly just for stacks if you needed it, matches X. 3, 5, 5, 6. What's the story with store? It's the same story. U and X match up, Y is 1 cycle longer. Load effective address? In this case, it's the same. In fact, I started taking this so seriously, I just blacklisted Y and decided never to use it. And at some point, I found myself actually using memory accesses and saving things on the stack when I actually had Y left over and I could have used it for some other purposes. So I realized I was overcompensating and then brought Y back into the game, but only as a last resort. ABX is one of the weird instructions on the 6809. It's got no variants. It only works with the B and X registers. There are no extra addressing modes. All it does is add B to X. A common place this is useful is avoiding indexed addressing when advancing a pointer. An actual example from my code loaded B with an offset value, loaded X with a pointer to the beginning of some memory, and then advanced X by that offset. The new code, the first 2 lines are identical. The only change is I'm using an ABX instead of LEAXBX. By doing it that way, I save 2 cycles. 5 for the LEAXBX and only 3 for the ABX. Since ABX only works with the B and X registers, this can lead you into habits. Generally let X be your first choice when you're indexing into memory. Let B be your first choice when it's an offset. This is especially handy when you have loops. If you can afford it, you can load B with, say, the size of a structure that you're iterating through in an array. And then each time through the loop, just do an ABX to move X to the next one. In cases where you're using a constant offset, it's actually even a wash if you spend the extra cycles to put that constant offset into B before doing the ABX versus just directly using 1, X in your LEAX instruction. If you count out the cycles, it totals 8 either way. But things get even more interesting when your offset's a bit bigger. In this example where the offset is 128, even though I'm doing the extra work to load B with that value before doing my ABX, I come out 3 cycles shorter this way. And the reason is that the cost of doing indexed addressing is dependent on the size of your index. We will talk more about that later. There is a potential gotcha here though. If you're using the B register as your index, LEAX will treat that register as a signed value. ABX always treats B as unsigned. So if you're ever intending this index to be negative, LEAX is the way to go. Unless you want to restructure everything so you're no longer depending on it being negative. The test instruction is a convenient way to test a certain area of memory by setting the condition code so you can use a conditional branch on it later on. I was using it all over in my code, checking, are you 0, are you positive, are you negative? But oddly enough, the load instruction can do the same thing for fewer cycles. Let's compare these 2 groups of code. In one group, I set condition codes based on this area of memory, and then I do a conditional branch. In the other, I just load the value of that memory into B and do the conditional branch. In both cases, the condition codes do get set, so this will do the same thing. But surely, since this is doing more, it will take more cycles. Nope. Using test takes a total of 10, whereas using the load takes a total of 8. And if we use direct mode addressing instead of extended mode, again we save 2 cycles. We're doing more and saving 2 cycles. Of course, we're not really doing more. This is how a software person would think of it. But a hardware person knows that it's more complicated than that. I presume. I'm not a hardware person, but I presume they would know that. I've heard there are these things called temporary registers that we as the programmers don't get to see, but that live in the CPU. And an instruction like this must be writing to those temporary registers for the purpose of setting the condition codes. And I guess the regular registers are more optimized for use, and so it's easier to load something into a regular register, have the condition codes be set off of that, than using test and these, I guess, temporary registers. Of course, there is a downside to this approach. You are trashing B. So if you've got all your registers in use and you can't afford to use one, then this might be your best option. But I was able to save a ton of cycles by not doing this and just using a register in the cases when I had one to spare. For this next one, take a look at what it takes to animate the car. It can move a bit to the right, it can move a bit to the left, and it can go up and down. When we make it move to the right, for example, it only moves to the right by 1 byte, so we don't have to spend time erasing the entire car and then redrawing the entire car to the right. We could just redraw the car to the right, and then maybe there's a little bit at the left we need to clear out. Similarly, when it's going to the left, there might just be a couple stripes at the right that we need to clear out. Similarly, when it's going up, there might just be some stripes at the bottom to get rid of, because as we redraw the car higher and higher, we're already overwriting the old location of most of the car. And when it comes back down, we only really need to erase some of the stripes at the top. So I wrote some code that would just be very careful about it. For example, as the car is falling back down, I erase 1 stripe above it, check to see if that was enough, and if not, I erase 1 more stripe. And the nice thing is you can't be jumping and sliding at the same time, so I don't even have to do any erasing for sliding. But if the car is sliding, either I erase 2 columns on the right side, or 1 column on the right side, or 2 columns on the left side, or 1 column on the left side. I'm just careful to look and compare where the car is now versus where it was before, so I can do as little work as possible. And doing the erasing isn't that much work anyway. Erasing 2 columns on the left is merely a matter of loading up a 2-byte register with the green bytes, and just storing it all the way down the left. But then I made some changes to the jump. And now when it jumps up, it doesn't just jump up by 1 or 2 lines, it jumps up possibly by several. This gives it a nice, more of a physical feel to it. But then that changed what I had to do when it came time to erasing, because my assumptions were no longer valid. So now when we're jumping up, it's not merely a matter of 1 or 2 stripes, it could be arbitrarily many stripes, or almost arbitrarily many. So now I have a loop. And I might have to do this several times, possibly almost the full height of the car, until we finally decide that yes, we're done. But still, sometimes the amount that we're jumping up or jumping down compared to where we were before will only be 1 or 2 lines. So much of the time, we actually will terminate that loop nice and early. It's only in the worst case where this loop is going to have to do the max number of iterations. And remember, we don't have to do any erasing for the sliding if we know that we're jumping. And we don't have to do any jump erasing if we know we're not jumping. I had a sneaking suspicion that I was kind of going along with an old outdated plan and I was being slowly boiled. So I said maybe it's time to take a step back and see the changes that I have brought forth. What have they wrought? So taking the jump up loop as an example, it's a total of 35 cycles each time through that loop. And the question is, how many times does that iterate? Well, it is variable, but I did some debugging to be absolutely certain, and it iterates 6 times, then 11 times in the next step, and then 9 times in the next step, then 7, then 6, then 5, then 3, and then finally 1. So I was surely gaining a lot that time when it was only 1, maybe even only 3 iterations. But 11 iterations, 9 iterations, and then repeat that again for the falling down loop, which does the same thing. So the real question here is, would I be better off if I just unwound the loop the maximum number of times it would have to iterate, and just always do that amount of work all the time? If I did that, I would be saving some work. The update of the loop variable, that cost me 4 cycles each iteration. I could just not do that at all. The compare and the branch, that's another 5 plus 3 cycles, gone for each iteration. In fact, all the conditional code that asks, am I jumping, then do this kind of erasing, and if I'm not jumping, then do this other kind of erasing, and check to see whether I've slid or not slid. If I just always erased the car and never asked how much to erase, never asked what kind of erasing to do, just erase the whole car every time, and in an unwound fashion, would I be better off? Once I allowed myself to do the maximum amount of work every time, and thus a predictable amount of work every time, I was able to start putting in other optimizations as well, like stack blasting. So here's my new completely unwound loop that does more work than it needs to almost all the time. But it's not a loop anymore. It's just a whole bunch of pushes and moves of U, pushes and moves of U. The new way, I'm spending how many cycles each time? 169. That is not nothing. But compare that to what I was doing before just for jumping up and down. 210, 385, 315, 245, 210, 175, 105, and 35. Overall, this is clearly a net gain, and I'm not even counting the cycles I saved by not having to do the specialized sliding erase of the stripes on the left and the right side. So the real lesson here is turning a variable amount of work into a predictable amount of work, even if that predictable amount of work is more sometimes than the variable amount of work, can save you cycles, especially if it eliminates a bunch of loop variables and loop conditions and branches. I found the indexed addressing mode table to be quite eye-opening. You can find this in the Darren Atkinson programming reference. And in particular, when you have a register and a constant offset from that register, the size of the offset affects how long that instruction takes. It was interesting to see that there's a difference between a 5-bit offset and an 8-bit offset. Not different in terms of speed, they'll both add an extra cycle for that instruction. But the 5-bit offset doesn't need any more bytes in the byte stream. Of course, right now all I really care about is speed, so the first threshold that's important is this. If I can keep my offset between -128 and 127, that's going to be the best non-zero offset I can do. Once I go outside of that range, I'm now adding 4 cycles instead of just 1. I've already discussed this in this past video, and there's a link in the description, but I think it's worth mentioning again. When I was erasing obstacles as they scroll by, this is how I was doing it before. Starting at offset 0 and then moving down the obstacle until I get to 13 lines below the top. I changed that so that I would have my pointer starting somewhere in the middle, so I could take advantage of negative and positive offsets all within that 8-bit range. I even had to do an adjustment of X. I had to add an instruction I didn't have before just so I could take advantage of it again, and it was still better. Looking at it visually, I used to have the pointer start here, and then I would just offset 32 times the line number to get all the way down. Now I start my pointer here, and then I can take in from -4 times 32 down to 3 times 32. Then take the time to adjust my pointer so it's down here so that I can start back up at -4 times 32 and continue on down. As I mentioned in that video, that took me from 146 cycles down to 134. That's 12 cycles saved, even accounting for the fact that I had to adjust my pointer midway through. Check out this change I made. I load my X. I do some math based on this size. I subtract that from X. And then I store the result back. Instead of X, I'm using D. Load D with the value. Now I'm doing a sub D instead of a load effective address. Still subtracting by the same amount. And then store that back again. Surely there's no difference between these two approaches, right? Oh, but there is. 20 cycles the first way, 16 cycles the second way. And the big culprit is this. It just so happens that the index we're using does not fit into 8 bits. Therefore, we're using this version of the indexed addressing, and we're adding an additional 4 cycles instead of 1. That gives us that +4 here. Meanwhile, sub D happily takes whatever size you give it, and for only 4 cycles completes its mission. In fact, even if this were a small offset, this would still be 4 + 1, and we still would have saved 1 cycle by doing it this approach. The 6809 is the first processor that I learned assembly on a long time ago, and then after I had done a bit of that as a kid, I then moved on to doing some amount of assembly on 68000 and x86. And in particular from x86, I started to get used to certain conveniences, like when I'm comparing two values, I can actually compare one register with another. And then recently, when I returned back to 6809, I found myself surprised on the 6809 I cannot compare two registers together. So take, for example, a division routine. Let's say I'm dividing A by B. One way to do this is to have a loop where you keep subtracting B from A until A is less than B. But you can't ask, is A less than B? One way around this is to store B into memory and then compare against that memory location. So the way this works is I store my B here, I then clear it, and B I'm going to use to hold the quotient. So I compare my dividend with the divisor I stored. If it's lower, we're done. Otherwise, I subtract the divisor from A. I'm really subtracting what used to be B from A. I increment my quotient, and then I loop back up. But there's another way to go. Rather than storing B into memory and using that, I could use the stack instead. Now, instead of storing B into memory, I'm pushing it onto the stack. And rather than comparing A with memory directly, I can compare A with what's at the top of the stack. If it's lower, I'm done. Otherwise, I subtract from A what is at the top of the stack. And the rest of this is the same, more or less. I do have to do a little funky business here to fix up the stack. I'm effectively pulling those 8 bits off before I try to return. So what's the difference? The most important part is the loop, so let's focus on that. In the first variant of this, the loop itself is 18 cycles per iteration. In particular, the compare and the subtract are each 5 cycles. In the second approach, the loop is now 16 cycles per iteration, because the compare and the subtract are only 4 cycles. This can be a nice win, but there are many caveats with this. First of all, the reason the compare and the subtract are so quick is because I am not using any offsets against S. That's why we have this +0 here. If instead I had a 5 or an 8-bit offset, I would be adding 1 to my cycle count. And if I add 1, then it becomes a wash, because now it's 5 cycles for the compare and the subtract, just like it is in the first approach. But it's worse than that, because the stuff before and after the loop isn't the same. Storing B into memory using extended mode addressing is 5 cycles. Pushing B onto the stack is 6. A simple return from the first approach is 5 cycles. But since I have to play around with the stack a bit, it's actually now 8 cycles. This means there's an overhead of 4 additional cycles in this approach. I save 2 cycles each time through the loop, so if I expect to go through the loop a couple times, then it's a wash, and if I go through the loop more than 2, then I should be gaining something. But again, only when I'm looking at the very top of the stack. I can't use this approach to push an arbitrary number of values onto the stack and use them all, because as soon as I need to index to get to any of the other ones, I'm now worse off because of the overhead. And finally, the reason this is a gain at all is because I was comparing it with extended mode addressing. If I use the direct page instead, now my compare and my subtract are 4 cycles. So now my loop equals what my loop would be when I'm just using the tippity top of the stack, but the stack approach does have that overhead before and after, so it's no longer worth it. This one really surprised me. Imagine, if you will, you're just a simple man looking through your code, and you're looking for places that you can convert LEAs into ABXs. And you come across this code, and sure enough, here we're updating our X, and maybe we can make that be an ABX, and then something catches your eye. We're looking at how X gets used, and we see we load A with the action for X, and our eyes happen to drift over here, and we see a 4 plus 4. 4 plus 4? But level progress entry action is very small, isn't it? And shouldn't this be a 4 plus 1 for a small index? And so you visit Darren Atkinson, and you say, Darren Atkinson, when I have a small offset, isn't it just a plus 1? And he says, yeah. And you say, well, when is it ever a plus 4? And he says, well, it's when it's a 16-bit offset. And you say, but surely that's not a 16-bit offset. Surely my action is just a tiny number. And you take a look at that structure, and sure enough, look at action. This can't possibly be a large offset. Why, this should be 2. 2 isn't big. And so you go back to that line and you ask, what got generated for the offset? And you scroll to the left. 2! But then what catches your eye? It's a full 16 bits to express that 2. Do my eyes deceive me? Is this using the 16-bit offset variant? That second byte is 89, and hex 89 is this in binary. Notice how it ends in a 1001, just like the 16-bit offset. What's going on? Why? Why hath you forsaken me, LWASM? And then it occurs to you. Is it possible that LWASM just didn't know that this could be a 5-bit offset? Could it have something to do with the order? So you try out a test. You add your instruction before you define your struct, and then you add that exact same instruction after you've defined the struct. Are these going to be assembled differently? Why, yes, they are. The first one, sure enough, still has that plus 4 with a full 16 bits for the 2. The second one is a mere plus 1, and it's a 5-bit encoding of 2 as the second byte, just as Darren Atkinson prophesized. And this is where I realized that my preconceived notions yet again have messed with my head. I'm very much used to using compilers, where compilers will either tell you you screwed up, or they will just succeed. And if they succeed, you can rest assured the compiler did everything possible to optimize the code as much as need be. But remember that compilers are creating the assembly that they will pass on to the assembler in the best possible way. Here I am hand authoring my assembly, and there may be rules that I'm not quite aware of, and if I break those rules, the assembler will do the best it can do, but it may not produce the most optimal code even if it succeeds. I can't rely on an error message to tell me that I could be a bit better. Now, I haven't looked at the source for LWASM, and I'm certainly no expert in writing assemblers since I've written exactly 0 of them in my lifetime. But as I understand it, LWASM does its work in 2 passes through your code. In the first pass, it needs to figure out the values of all of your constants. And that means it's going to need to know the size of the code. Otherwise, how could it know the address of labels that you give it? So during the first pass, if it hasn't encountered this yet, it's going to make the worst case scenario assumption that it's going to take a full 16 bits to encode this, and therefore it's going to use the 16-bit index. That way, no matter what this turns out to be, it will definitely work. But later on in the first pass, this line has the benefit of being after the definition, And LWASM knows, oh, this can definitely fit in that 5-bit index, so I'm just going to do it that way. Now that said, there are hints that I didn't know about at the time that you can apply to force a particular size of index. In particular, in my case, I could do this. And this says, I know this is 5-bit, please do it 5-bit, don't do it any other way. And now when we look at the generated code, they're both a +1. And if we look at the generated code, sure enough, it's the 5-bit index. But what if I lie? Bam! What's that gonna do? Now our action is gonna be hex 300. Aha! So LWASM is smart enough to know if we lie to it. And it will tell us, dude, byte overflow, I'm not going to compile this. And it knows it for both of those lines. So there are a couple ways around this issue, and one of them is to just make sure that all of your definitions are at the top. That way LWASM will automatically pick the most efficient way to encode the instruction. The other way is to make your intention known explicitly every single time you use indexed addressing. That seems like a lot of work. After I moved all of my definitions to the very top, I was so surprised at the result. With my source code just before I reordered everything, after I assembled, I end up at 6A74 with these 7 bytes. So my code ended at 6A74 plus 7. What did it look like after I reordered everything, and only reordered everything, did not do any other change? Now the code ends at 69E6 plus 7 bytes. That is a difference of 142 bytes, which would be 71 words. Now I don't know what all of those words are. I don't know for a fact that this is predominantly shortened because of all the indexed addressing, but quite possibly. And if there are 71 indexed addressing instructions that got changed to 5-bit or even 8-bit addressing, that's over 200 cycles. 200 wasted cycles just because of the order I happened to write my code. And now the moment you have been waiting for without realizing that you have been waiting for it. All of these optimizations that you have seen me discuss, I actually only recently applied to the game. So I can show you a comparison of before the optimizations and after. So I've got both versions of the game running in autopilot mode and the new MAME meters in full force. One thing you might notice is that the after on the right actually does look a bit faster, but don't let that fool you. That's merely because as I was going through my optimizations, I decided I didn't want to drop as many frames as I was dropping. So I got rid of one of the syncs so that the frames would go a bit faster. So that actually has nothing to do with the optimizations I've done. But what does have something to do with the optimizations I've done is the average meters. Look at the lower left meter on both versions of the game. A higher number, a higher bar is better. That implies that more of the frame was remaining to be drawn by the time we reached the end of the main loop. And that means we were able to get more of our work done in less time when that bar is higher. So let's see how this averages out over a few minutes. The final average meters show 19.9% before and 30.0% after. Since these are percentages of a frame, and a frame has about 262 scan lines, then converting this to scan lines yields about 52 scan lines remaining to be drawn in the before, and 79 scan lines remaining to be drawn in the after. There are about 57 cycles per scan line, so that means 2,964 cycles before the screen was fully drawn in the before, as compared with 4,503 cycles before the screen was fully drawn in the after. In other words, 1,539 cycles were saved every single frame as a result of these optimizations. This is a testament to how great an optimizer I am, or more likely, how poor a first draft of code writer I am. I hope you found that interesting. I know I certainly have over these months as I've discovered these ways to optimize code. As always, thank you for watching.